Hey there, and welcome back to How'd You Get That? We are solving today this problem. Find the inverse function of f of x is equal to x squared over x plus 1 along the interval x is greater than or equal to 0. Eventually, we'll also verify this using the relationship f of inverse f of x is equal to x. First, let's take a look at the stipulation that x must be greater than or equal to 0. If we graph this rational function, x squared over x plus 1, we get this graph. And we can see that this function does not pass the horizontal line test. Now that's okay. A function doesn't need to pass the horizontal line test. But in order to have an inverse along all its domain, it must pass the horizontal line test. So we can see that if we only define this function along the interval 0 to positive infinity, then it does pass the horizontal line test, and we can come up with an inverse function for this original function. The first thing I do is rewrite the function in terms of y, so y is equal to x squared over x plus 1, and then I swap my x and my y, and personally I like to replace the y with y star. So I get x is equal to y star squared over y star plus 1. I now have to solve for y star. How do I do that? Well, the first thing I could do is I could just cross multiply, so I get x times y star plus 1 is equal to y star squared. And then I can distribute that x, so x times y star plus x is equal to y star squared. And now we see that we sort of have a quadratic relationship here because we want to solve for y star. That's our ultimate goal here. So if I write this as a quadratic with respect to y star, I get this. 0 is equal to y star squared minus xy star minus 1. Now this looks just like a quadratic that we could solve with the quadratic formula, where we're gonna solve for y star. And in this function, a is 1, b is negative x, and c is also negative x. So we get y star plugging into the quadratic formula is equal to x plus or minus the square root of x squared plus 4x all over 2. Now that's basically it, except we still need to handle this plus or minus sign in there. So let's go back to that added stipulation that x must be greater than or equal to 0 in our initial function. The domain for the original function that we've defined is from 0 inclusive to positive infinity. If we look at the graph, we can see that its range is also from 0 inclusive to positive infinity. And remember that inverse functions flip the domain and range of the original function. So the domain of the inverse function is from 0 inclusive to positive infinity, and its range is also 0 inclusive to positive infinity. Now let's take a look at which solution to this quadratic formula fits, the x plus the square root over 2 or x minus the square root over 2. Now if I take the inverse function along the domain on which we are defining it from 0 inclusive to positive infinity, I basically can just plug in any positive value for x. And I can see that if I plug in a positive value for x and use the minus solution to this quadratic formula, I actually have the potential to get a negative answer. But if I plug in a positive value for x and then use the positive solution to this quadratic formula, I'm always going to get a positive solution for y star, which is exactly what we want. We are defining that y star exists in the range from 0 inclusive to positive infinity. So since the plus solution to the quadratic solution is the only one that always gives us a positive or 0 value for y star when x is also positive or 0, then this is the solution that we want to go with. So our final solution is that inverse f of x is equal to x plus the square root of x squared plus 4x over 2. Okay, a little bit of a mouthful, but that's okay. That's actually the inverse function along this domain. Now let's try to verify this using f of inverse f of x is equal to x. Now remember, our original function f is x squared over x plus 1. So wherever we see x, we need to plug in inverse f of x. So inverse f of x squared over inverse f of x plus 1 should equal x. Now, if I now replace inverse f of x with what we just found inverse f of x to be, then I get this result. Now, I just need to do a little bit of algebraic manipulation here. Remember, in the top, we're going to FOIL this, which is a little daunting at first, but remember, we're just gonna have 3 terms. We're gonna have an x squared term, we're going to have a middle term that incorporates the root, and we're going to square the root at the end. And it looks like this. In the bottom, all we need to do is convert 1 into 2 over 2, so we get a common denominator between those 2 fractions in the denominator. So we can reduce the numerator a little bit like this, and we can reduce the denominator a little bit like this. Now we have 2 individual fractions, 1 in the numerator and 1 in the denominator. Now remember that division is just multiplication by the reciprocal. So I can take the denominator, put it outside the whole fraction, and flip it over. And we can see that the 4 partially cancels with the 2, and I can make this fraction. I can distribute that 2 that's now in the denominator through the parentheses, and I get this result. Now see, in the numerator, there is a factor of x in every term. That means I can factor out that x and write it like this. Now look, in the numerator, I have this factor here, which is exactly the same as the single factor in the denominator. That means that this part of the numerator cancels with this part of the denominator, and I'm just left on the other side with x. Now we've shown that indeed these 2 functions, f of x and inverse f of x, are inverses of each other, using the relationship f of inverse f of x is equal to x. If you have any questions, leave them in the comments below, along with any suggestions you might have for future episodes of How'd You Get That? Hit that like button, subscribe, and hit that notification bell so you never miss another math, physics, or problem-solving tutorial. Thanks so much for watching, and I'll see you in the next problem.